in some greedy algorithms, you usually kind of want to do some ordering such that it's the optimal ordering. You're trying to minimize a total cost. So I'm going to show the exchange argument of proving such greedy algorithms are optimal. So I'm going to make use of the discussion 6 service scheduling problem. Here we have n customers that are waiting in line, such that each customer is going to require a certain amount of time. And if I want to minimize the total wait time, and the wait time for a customer is going to be the total amount of time of the customers it takes to serve all the customers before me in that ordering, right? So if I had 1, 2, 3, 4 customers like this, and my ordering are, let's see, something like this, let's say my times. Then for customer 1, there's 0 wait time. For customer 2, there's a wait time of T1. Customer 3 has wait time of T1 and T2. And customer 4 has wait time of T1, T2, and T3. And so we want to minimize the time that we spent in total, right? The total cost of all customers waiting. We want to minimize that total cost. So how do we compute the optimal order to process all the customers in the most efficient way possible? So let's consider this. If I had, let's say, this example right here, right? If I had this one as very long, it takes very long to serve customer 1, then all these 2, 3, and 4, they all have to wait for a T of 1, which is super long, right? Whereas if I take these smaller ones before the long one, then this guy no longer has to wait for the long one, neither do these two. So if you look at this point in time, I would have served only one customer in this ordering, whereas I would have served all 3 of these customers already. And since I've served more customer at a certain period of time, that means less total wait time, right? Because these 3 customers no longer have to wait for this amount of time anymore, right? And that's more efficient. So we kind of want to just do increasing order of by T of I. And so that's going to be our efficient way. That's going to be the efficient solution that's going to give us the most optimal ordering and minimize my cost. Now, now consider this. For any ordering, let's define the time of T. For any ordering, we have S of J. Oh, let's not call it S. Let's call it P of J. So the position of customer J in any ordering, right? This is the position of customer J. Customer. Now, my total cost, time, is going to be for every customer, the time spent waiting by this customer is going to be all the customers before me, right? Before I, for some I, all the customers before I, such that I sum up all their times, right? So for customer 3 here, I sum up all the times for customers before me, which is 1 and 2 in this case. Which we can reword it kind of as the summation of all the customers. So for a certain number of customers, for a certain customer, let's say T of I in this case, this T of I the waiting time gets propagated to all the customers behind you. So if we have this many number of customers behind you, then we will have, then this is the waiting time, this is the number of times we're going to add T of I to our total waiting time. So this is 2 ways to think about the time cost. Now let's prove why this is optimal, right? So let's say we had our original ordering, 1, 2, 3, 4, and let's call S of I as the sorted ordering. In this case, we have S1, S2, S3, S4. and that this is going to be 4. Let's say this is going to be 3, this is 1, and this is 2. Okay, so let's say this translates to this sorted ordering. And now we see that in our original ordering, we have something that's out of order, right? Now suppose that I take this original ordering and I take 2 elements that are out of order. And by out of order, I mean the time of S of I is going to be greater than the time of the order of S of j, right? So my ordering, we have this case such that I comes before j. Right. The time it takes for I is going to be greater, but I is before j. So it's something like this. Right? So we have I and j here. And we want to go down to j of I like this. So what happens to my cost? Okay, so if I switch I and j, both I and j have to wait for this amount of time anyway. So this won't matter, and it's kind of the same as switching 2 adjacent pairs. So if I were to move I behind j, now j no longer has to wait for i's time. But since I comes behind j, I now has to wait for j's time, right? So this is t, that's called old. But this is always going to be less than or equal to the original time that we had, because I'm subtracting a larger number here and adding a smaller number. So we guarantee that this is going to be less than the time. So we're going to have an improvement. So if I take any pair such that this occurs, right? We have this condition where they're misplaced so at every single step, I have some ordering, and I take 2 pairs that are misplaced such that the element that comes before you has a greater time, right? If we were to exchange these two arguments, we're gonna always have an improved time, right? We could always just add those inequalities in here, so we're gonna make them with a lesser. We're gonna add the inequalities so that equality could occur, right? So if I were to switch any of these, your time is always going to be improving, right? So if they're equal, then your time can't, at worst, can't be larger. Which means that if I take an element like this, I just move this element until I get to a place where this no longer occurs. I can do this for all the elements, and this is kind of like bubble sort, right? If I bubble sort this way, then you know that when you're bubble sorting, you take 2 pairs, you compare. If the time is greater and we come before it, then we switch it. By switching, the new time can't be worse than the old time. So at every single step, our total cost either stays the same or it's going to improve. So what happens is that at our final sorted ordering, we can't improve this time anymore, right? Because we don't have any of these conditions left. And if we're to exchange the other way, then our time can only be worse off. So once we have this means that we have our optimal ordering as exchanging any 2 elements cannot improve my time or improve total cost. Right. And if I can improve my total cost, then we have a global, global minimum for this solution or global optimal solution by this exchange argument.